Let's go ahead and begin our 10.4 notes, which is on biconditionals and definitions. So, the first thing we need to know is what is a biconditional statement? Biconditional statement. Biconditionals have two parts as well. It's very similar to a conditional statement that has an if and a then, except these have two parts and the words, the key words, are in the middle. Have two parts and the key words are in the middle. What are the keywords? I'm going to put it in quotations. If and only if. Biconditionals have the words if and only if in the middle of its two parts. When you are writing a biconditional statement, because this is used not just in this class, but it's also used in future classes, you can abbreviate it. The common mathematical way to abbreviate this. This is how we abbreviate it. I'm going to put it right here. I, F, F. I'm going to highlight that. It's like this. If. That's how I say it in my mind when I see it. If. I don't know. It's funnier in my mind, I guess. Okay? If and only if, we're going to abbreviate it as IFF. If you ever want to write out if and only if, you can just write IFF, and I'm okay with that. And that's the only thing we can abbreviate at this point. Okay? Biconditionals have two parts, and they have the words if and only if in it. This means that the converse is also true. So here's my example for you. My example is this, of a biconditional. What's a biconditional? I already have it here, but here's an example of what a biconditional looks like. A triangle is equilateral, IFF. Let me scoot that up just a little bit for you. A triangle is equilateral if and only if it has three equal sides. So what this is saying is a triangle is equilateral. This is your first part. The key words are in the middle. If and only if it has three equal sides. You can test whether this is true and think a triangle is equilateral if and only if it has three equal sides. If it has 3 equal sides, let's do the converse. If it has 3 equal sides, then it's equilateral. Does that make sense to you? If it has 3 equal sides, if a triangle has 3 equal sides, then it is equilateral. Is that true? If it's true going this way, or if the converse is true, then this is a true biconditional statement. What you are going to have to do is you're going to have to read biconditional statements and then state whether they are true or whether they are false. And then if they're false, you're going to have to provide a counterexample like you've been doing. Okay? Okay. So in numbers 1, 2, 3 on your worksheet, you're going to have to write converses. So I don't feel like I need to, I'm just going to put this on your notes. Numbers 1 through 3, use your notes from 10.3. That's what I want you to do on numbers 1, 2, and 3. Use your notes from 10.3. That's no big deal. It's review. Number 4, and number 5, you're going to have to split some things up. You're going to have to figure out what the 2 statements are that form each biconditional and just use proper English as best you can. So let's do number 4 together. Number 4, if you do not want to write this example down, I'll understand. But you can write down what the answer is. That'll be just fine. The product of 2 numbers is a perfect square if the 2 numbers are identical. The product of 2 numbers is a perfect square if and only if the 2 numbers are identical. So it's going to ask you to write the 2 statements that form each biconditional. So we have to split this up into the 2 statements. Write as 2 statements. Write as 2 statements. That's what our directions will say. So I look at the IFF. I put my thumb over it. I kind of cover up everything that follows the IFFF. Whatever that is. I think I said one too many. The product of 2 numbers is a perfect square. That's your first statement. That's statement number 1. So what's statement number 2? The 2 numbers are identical. So all you're going to have to do is to write out 2 sentences from the biconditional statement. Okay? Sentence number 1. The product of 2 numbers is a perfect square. Statement number 2 should be pretty easy. What am I going to write? Anybody? Exactly. The 2 numbers are identical. That's it. That's how you do number 4. Let's talk about reversible. Reversible means is the converse is reversible means that the statement is true and the converse is true. Something is reversible if you think it's true going the first way, if and then, and if you do the converse and you switch it, and the converse is also true, then it's reversible. And your worksheet today is going to ask you to see, is this reversible? So I'm going to give you an example like number 6. Is it reversible? A linear pair consists of two angles with measures that sum to 180 degrees. And the question is it reversible? A linear pair consists of two angles with measures that sum to 180 degrees. A linear pair consists of angles with measures that sum to 180 degrees. So the first thing I want to check is this a true statement? A linear pair consists of two angles with measures that sum to 180 degrees. If I have one angle and it's like this, and I have another angle and it's like this, and let's say this is 60 and this is 120, is that a linear pair? Doesn't matter. If you read what the definition of a linear pair is, a linear pair are two angles that sum to 180 degrees. That's the definition of a linear pair. If you're not sure, you can always look it up in your math book. You can look back in the glossary and find out what it means. But two angles that add to 180, that's the definition of a linear pair. Okay? A linear pair consists of two angles with measures that sum to 180 degrees. That's its definition. Second thing I'm checking, is this reversible? Is the converse also true? If I have two angles that sum to 180, if they add to 180 degrees, if two angles add to 180 degrees, then it's a linear pair. Is that also true? If two angles add to 180, then it's a linear pair. Is that also true? Yes, it is. That means that this is reversible. Sometimes you're going to have to really think about when you're doing a reversible statement. You're going to have to think about, how could I write this in a different way? A linear pair consists of the definition of a linear pair is something that has two angles with measures that sum to 180 degrees. I have to kind of put words into it sometimes for it to make sense to me. Last thing that we're going to be really writing about before we go to our example, I'm going to have to turn this page over because I'm running out of room. Is what is a good definition? A good definition is one that uses clearly understood terms is precise and is reversible. That's not very square up there. Let me center that. Uses clearly understood terms, is precise, and reversible. Sometimes it is biconditional. And you are going to have to use common sense when you start 10.4. When you start 10.4, you are going to have to use common sense whether something is a good definition or whether it's not a good definition. Sometimes you might have to look something up to figure out what does this word mean. You might need to use dictionaries and glossaries or Google, the way some of you use technology today. Let me give you an example. Let's see. I'm going to use number 11. Opposite rays. Look at Ray. You're in a problem. Opposite rays. Actually, we have two rays in this class. That's pretty fun. Opposite rays are two rays that share the same endpoint. Let's scoot that up a little bit. Opposite rays are two rays that share the same endpoint. So you may or may not remember that I've already defined what an opposite ray is, but it's in chapter 7, and we're in chapter 10 right now, or unit 10. If you've forgotten something that I've already taught you, you may have to look back at previous notes. You might have to look up things on your phone, or you might have to do some sort of legwork before you make your decisions, or ask somebody in class who you think knows. Opposite rays. I hope you know what opposite rays look like. I hope you know that two opposite rays, when you see them, forms a straight line. That's what I'm hoping you remember. Opposite rays are two rays that share the same endpoint, and the directions are going to say, is each statement below a good definition? If not, explain. Is it a good definition? That's the question. Definition. Opposite rays are two rays that share the same endpoint. Is this a good definition? They have to just share the same endpoint for them to be opposite rays.
Yes.
No, it isn't. Because two lines can share the same endpoint. Well, like two segments can share the same endpoint.
Okay, you're really close. You're not using the right words for me. I do agree that this is it's not a good definition. Not a good definition. This is not specific enough. It's not precise enough. Because I can think of a counterexample right now of two rays that share the same endpoint that are not opposite rays. Here's the counterexample. Just going to draw a picture. Good. You're right on the same wavelength as me. Here's a ray. Here's an endpoint. Those of you who don't remember, the endpoint is where it begins. It's the part that has an ending. The other part of the ray goes forever and ever and ever in that direction. Here's a ray that has an endpoint, and it's the same endpoint. Two rays that share the same endpoint. Here's an example of two rays that share the same endpoint. Does this form opposite rays? No. What should opposite rays look like? It should look like this. Here's the endpoint. One goes one direction. The other one goes the other direction. That's what it should look like. This is a counterexample. It's not a good definition because of this counterexample. Counterexample. Should be. We're going to stop right there with our notes.